Yep, you already figured out the filter, so you're good.
Thanks.
Okay, so our next talk this morning is about Boltzmann sampling of directed acyclic graphs by Zbigniew Golebiewski. I had that written and I said wrongly, so I'm sorry, but please go ahead.
Thank you for introduction. This is joint work with my student Wojciech Golebiewski from Wrocław University of Science and Technology. As you can see already from the title, we can start either justifying why direct acyclic graphs are such an important structure. But since I always wanted to contribute something to Boltzmann's Boltzmann sampling toolbox, I will rather go with sampling. So what we want to do, we want to sample uniformly as a combinatorial structure from a class, and throughout this talk, it will be always labeled structures. So let's C be a class of such structures, and Cn will be structures of size n with, oops, not this one, with cardinality small cn. Then the goal is to draw some gamma structure in a uniform manner. And there is many known methods to do this thing. Among them are bijective method, when you find the bijection with some simple structure, draw the simple one, let's say, and then try to use the bijection to go to the one that you need. Or surjective method, when you find a bigger set with the many-to-one relation to the structures that you need, and then draw from the bigger set. Or rejection methods, when you also draw from a bigger set and then reject the samples that do not meet the conditions that you need for your structure. There is Markov chain method, in which you start with some kind of initial configuration of your structure and then do some steps in a Markovian way to end up with uniformly distribution on the structure. There is recursive method, which usually needs some kind of decomposition and some kind of recurrence on the structure to be exploited. And there is also Boltzmann sampling method. So Boltzmann sampling was proposed by Duchamp, Flageolet, Louchard, and Schoffer in 2004, and it is based on the so-called Boltzmann model, which is stated that you give this parameterized probability of a given gamma structure with parameter z, which is just z to the size of the structure. Since we are in labeled world, then this is exponential thing, so we get this size factorial and also times the exponential generating function of those structures. And this, together with the backed up by the symbolic method and the combinatorial specification and all those operations like disjoint union, set, sequence, cycle, and so on and so forth, allows us to produce combinatorial structures in a uniform way. Maybe why uniform? This is like, for instance, in the Markov chain method, you start with a structure that is of a given size that you need, and you try to do as you make steps repeatedly as far as you need to reach something that is close to the uniform distribution. Here there is a different approach. You start with uniform distribution by design because of this Boltzmann model, but the size of a structure that you will end up is a random variable. So this is like kind of different approach. Okay, so in this 2004 paper, authors gives those how you should sample structures that are described by those set of rules. So starting with the simplest case, if you got a empty structure or one element structure, you just output this empty set or this element. If you got disjoint union of A and B, then you first draw a 1 or 0 from the Bernoulli distribution with this parameter, and then if you draw 1, then you again runs the Boltzmann sampler for A structure, and otherwise Boltzmann sampler for B structure. In case of products of A and B, you just return the tuple of Boltzmann sampler of A structure and Boltzmann sampler of B structure. And when it gets a bit more interesting, when you go to the sequences of A structures, then first you random a number from geometric distribution with the parameter A of Z. And then having this number, you produce a tuple of this size of A structures. So we run multiple Boltzmann samplers of A structures. And similarly for sets, you do more or less the same, but you draw a number from Poisson distribution. And for cycles, you draw a number from logarithmic distribution. So that was all nice, but if we would like to sample directed acyclic graphs, it would be a problematic thing to go with the exponential sampler, because the asymptotic number of the DAX is something like 2 to the n choose 2, some constant, n factorial, and here we got some exponential factor. So it is growing too fast for the exponential generating function. And that is why people already in the 90s introduced so-called graphic generating function, which is this one. So in fact, what you do, you add this this thing in the denominator. And also it is two variable function, and where Z marks the number of vertices of a graph and W marks number of edges of a graph. And with this generating function, some of the operations naturally extends, like disjoint union, pointing, distinguishing some specific subset of items, inclusion exclusion process, and so on. But in case of product of two structures that got those associated with those graphic generating functions, already Robinson in 90s, Gessel, and more recently Elie de Panafier and Sergei Zovgal gave a combinatorial interpretation of this product of graphic generating functions. They called it arrow product, and I borrowed this illustration from the Elie and Sergei paper. When you just have the structure, the graph structure from A, the graph structure from B, and then you connect the vertices from A to B by arbitrary amount of edges. I don't know if you see those edges in between A and B are red, supposed to be red, as the new edges. So what was also done, we can specify a graphic generating function for set of disconnected vertices. So this is just simple stuff because we got one such set and the rest is from the definition. And then they showed that a generating function of directed acyclic graphs is given by this simple looking equation. And moreover, if you want to mark the sources in this directed acyclic graph, you can do it and you end up with this nice looking equation. Okay, so our idea was, let's use this arrow product and those graphic generating functions to build a Boltzmann sampler of directed acyclic graphs. So first of all, we have to introduce the Boltzmann model for graphic generating function, which is more or less the same as it was before, but we just have to add this thing in the denominator, 1 plus W and here you got the number of vertices of gamma, choose 2, and also W to the number of edges in the numerator. Since now for some moment I will do not care about number of edges, so I just set W equal 1, and this simplifies to this parameterized probability equation. So when you start with those equations from this previous slide, you pretty soon end up showing that, for instance, if you got A and B and C classes of graphs, and C is just a arrow product of A and B, then there's probability of gamma that is from C is just probability of alpha from A times probability of beta from B times this this thing which is in fact telling us in how many ways we can assign the labels for alpha structure and beta structure, and also this additional term that tells us about the probability of the vertices from the about the probability of edges from the vertices from alpha to the vertices from beta. So having this, it is pretty easy to see that the Boltzmann sampler for arrow product can be done in these 3 lines. So first of all, you produce Boltzmann sampler of A structure and Boltzmann sampler of B structure, relabel vertices randomly, and then generate random arcs from vertices from A to the vertices from B with this probability of an arc 1/2, which is the consequence exactly of this thing. So if we start with our DAG function, DAG equation for a function for direct acyclic graph, we can work with this formula and end up with such formula when we can see first of all that here we get product of, so it is arrow product of k sets of this disconnected sets of sizes n1 up to nk, and this is nice because we got arrow product Boltzmann sampler, but we can also see this -1 to some power in front of it, which usually means that we probably will have to deal with some inclusion-exclusion thing. And in fact, it's easy to see that if you get this let's say this kind of directed acyclic graph, then you can decompose it into those sets of vertices in many different ways. For instance, here you got 2 different ways how to decompose this graph. So this was a problem because we wanted to have nice, clean algorithm like all the previous Boltzmann things were. And we do not do, if someone is doing something in something combinatorial structure, you usually know that inclusion and exclusion is messing things up, and this is usually a problem. So in order to avoid this problem, we have to came up with some kind of unique DAG decomposition, and this unique decomposition can be obtained pretty easily. You just repeatedly remove sources from this directed acyclic graph and put them to the next sets of disconnected vertices. So in this case, we start with the only source which is 1, put it to the first set. Then we forget about 1 in a graph and find new sources which are 2 and 3. Put to the next set of disconnected vertices, forget about 2 and 3, and find the next sources which are 5 and 4, and so on and so forth. And we end up with this kind of decomposition. First of all, this decomposition is unique. It is easy to justify by this construction, and also what we can see that this decomposition is kind of special, because for every vertex in some set, you have to have at least one arc from the vertex from the previous set pointing to it. So when we came up with this decomposition, we thought it's too natural and too easy to be like new thing, and obviously it is already known from many years, and in fact it was already used in samplers of directed acyclic graphs, the recursive ones, because you can also find the formulas exactly that says how this decomposition works. So this is maybe a good moment to say something about previous works. So like one of the first papers that we found about generating uniform random DAX was by Melancon, Dutour, and Miraguz-Kemalou from 2001. And they used, they provided really nice and simple algorithm this was Markov chain method. And they provided simple algorithm that was very, very easy to implement and so on. But the problem was that they even stated this in a paper, that the problem of finding how long the chain has to be iterated in order to be epsilon close to the uniform distribution is a difficult one. As we already seen on Tuesday, I think, even simple looking Markov chains, the mixing time might be very hard to get. So this was one of the problems of their approach, and they did some experiments, and they later state that assuming that Markov chain stabilizes after Cn to the power 2 steps, then the algorithm has worst case complexity O of n to the 4. Later, Kuipers and Mofa, they wrote this nice paper in which they first try to find some bound for the mixing time of this previous approach, and the bound they found gives them this kind of worst case complexity, so a bit worse than the one that was given in the 2001 paper. So they said that they also provided this recursive approach, which more or less works with the same decomposition that I told you before. And they state this sentence that the uniform directed acyclic graphs can be recursively sampled from scratch with n to the 5 complexity, which is marginally better than the Markov complexity that they were able to provide. So what is the problem? We already know what is the problem with Markov chain method, and what is the problem with recursive samplers. Usually, in order to do the recursive sampler, you have to have pretty expensive, let's say, complex in a complex way pre-processing, in which you have to count all the numbers for different decompositions and so on and so forth of the structure, and that is why it's end up with this n to the 5 complexity. They also provide some hybrid algorithm, which is kind of mixture of the recursive and then the Markov approach, which they claim that is O to the n to the 3 log n worst case. Later on, Martin Pepin and Alfredo Viola in 2023, they were working on a bit different structure, not the directed acyclic graph, but so-called directed ordered acyclic graph, when the order of the edges from that comes from the vertex matters, and they provide the recursive sampler for it, which uses slightly different decomposition of a graph. And like last half a page of the nice paper is that you can more or less go along the same lines with the recursive sampler for ordinary, for just normal directed acyclic graphs. And what they state in the paper is that they approach, in particular, this gives access to a polynomial time algorithm for sampling labeled DAGs with small bounded degree, which they say that is better than the previous approaches. So the other thing that was kind of taken on in the last paper was that maybe we do not only want to think about the number of vertices in this DAG, but also about the number of edges. So maybe we wanted to draw uniformly at random from directed graphs with given amount of vertices and given amount of edges, which was not covered, more or less not covered by the previous approaches. So, okay, I have to be hurry. So when we start working with all the formulas for directed acyclic graphs and also for the Boltzmann model, we could end up with this probability that the first set of disjoint vertices is given by this not so bad formula, I would say. And even more, we were able to provide formulas that the probability that the first set up to k set, you got some sizes n1 up to nk, and the k plus 1 set is empty. This allows us to show that, in fact, what was crucial thing, that in fact, if you wanna know what is the probability of the size of the ith set in the decomposition, it in fact depends only on the previous the size of the previous set. So this gives us this kind of Markovian behavior, and we were able to show how this probability will end up also with those from those formulas. In fact, those formulas here, there is like 2 pages long derivation of them, but I don't want to go into technical details of this. And this altogether gives us a Boltzmann sampler for directed acyclic graphs. For now, we care only about a number of vertices, and we do not care about the edges. That's why W is 1. So the sampler is pretty straightforward. First, we draw a number of sources in our graph. So the number of the vertices in the first set, exactly from the distribution that we were able to calculate. We create those vertices, and then we create next sets of vertices with the next probability distribution that we were able to calculate. And after creating next set, we also have to create the arcs from the previous set to this one, which are given in such a way that we, first of all, an arc is created with probability 1/2. It comes from these formulas, but also we have to, if we think about the 2 sets that are consecutive, we have to take care of this, that every vertex in a current set has to be pointed by at least 1 edge from the vertex from the previous set. And also later we add some more edges from the sets that were before, also with probability 1/2, and this also comes from the formulas that we get here. And then we iterate it as long as we end up with empty set. After all, we just randomly relabel all the vertices. Okay, so this is what I showed you is so-called free sampler. So we end up with some kind of more or less unknown for now size of a graph, and in order to be close to the size that we need, we have to tune it. So what this means that we have to choose the z parameter in such a way that the expected value of the size of the structure that we draw is n, the thing that we need. And we can also provide the formulas that gives us how we have to choose the z parameter in order to this equality be true. And you can see that, for instance, if we want to have something about 100 vertices, then we have to choose a parameter that is about 1.47 or something. Then this red dotted line is just a singularity of the graphic generating function of the direct acyclic graph, so we cannot go above it. This is one of the graphs that I was able to produce with this sampler. I'm not as good as Benedict, for instance, in visualizing graphs, so I'm sorry. You probably cannot tell if it's directed acyclic or not, but never mind. It got 45 vertices. This one got 17 vertices, and here you maybe can already tell that it's a directed acyclic graph. It is structured in such a way. And also this graph got 73 edges, which means this is kind of like average graph that you can get, because the average number of edges in random graph is what I did is n square over 4, and if you take 17 square over 4, then you get something about 73. Okay, so our next idea was, so let's go and try to incorporate the taking care of the number of edges in our sampler. So we go back to the original definition of this Boltzmann model for graphic generating function with two parameters z and w, and in fact doing analogous derivations from the formulas, but the formulas are a bit more complex. We were able to more or less derive similar formulas as before, which allows us to produce to give the Boltzmann sampler of direct acyclic graphs, in which parameter z corresponds to taking care of a number of vertices, and parameter w corresponds to edges. And here in red, you can see the changes from the previous Boltzmann sampler. So the changes are, I would say, pretty subtle, because you only change most of the 2's by 1 plus w in those formulas. And also the probability of creating an arc, before it was 1/2, and now is w over 1 plus w. And all those things, all those probabilities and so on, they came up, they pop up in the formulas that we were deriving. So this is, for instance, the graph that I was able to generate, which is also have 17 vertices, but I was generating it in such a way to get way less edges than on average. So this one got only 45 edges, the one before got like 73 edges. So we can already see that it's very different graph. Okay, so what's the future work? First of all, exact size sampling is the thing that we wanted. So usually this means that we Boltzmann sample structure and reject them until we get the size that we need. And we are right now, what we are doing is trying to somehow make some simple changes that allows us to give even more effective Boltzmann samplers in the rejection sampling case. So this free sample that I showed you here, it is on average n square, O to the n square, and I think we we are almost sure that we will be able to provide a sampler for exact size sampling that will be maybe also O n square. Maybe there will be some a bit bigger constant, but not much than O to the 3. And also the second thing is that in those papers from the 90s and the paper by Eli Depanafie and Sergei Dovgal, they showed that different directed graphs can be obtained. You can obtain the formulas for different directed graphs, for instance, strongly connected digraphs with this graphical generating function. And we wanted to also to use it to build the samplers for some different directed graphs. But for instance, in this case, we have to deal with the exponential Hadamard product, which is a bit a pain, and still we are still working on it. And also the last thing that I want to mention is that Boltzmann sampler are also used in order to analyze some parameters of structures, and we hope that we can use those samplers to analyze some new parameters of directed acyclic graphs. Thank you. That's all.
So one very quick